In this video, we are going to look at how we can determine the empirical formula, molecular formula. The first example I will look at is if you are talking about a molecular formula. This is a formula showing the number of each type of atoms in a molecule. And then the empirical formula shows the simplest whole number ratio of the atoms in a compound. For example, if you look at acetylene, or we can call it ethine, its molecular formula is C2H2, and if you look at the structure formula showing the atoms bonded to each other, it is H, C, triple bond, C, single bond H. So the empirical formula will have only CH, which means that we are only showing that there is one carbon and hydrogen atom. Yet the molecular formula shows the actual number of atoms that are going to be in the molecule. So instead of writing C1H1, we just write CH to show the empirical formula. Okay, so we can give a more detailed view of the definition of the empirical formula. The empirical formula represents the simplest whole number ratio of various atoms present in a compound. Okay, and if you look at an example of glucose, the formula is C6H12O6, but the empirical formula is going to be CH2O. Now, for obtaining empirical formula and molecular formulas of a compound, we can follow these steps as below. One, we shall need to, for example, if you look at a problem, a compound contains 4.07 hydrogen, 24.27% carbon, and 71.65 chlorine. Its molar mass is 98.96 grams. What are the empirical formula and molecular formula of these compounds? So we shall start by listing the elements that are present, and then after listing those elements, we are going to divide these percentages that I've underlined here. We shall divide them with their atomic masses. So this mass that have been given as 98.96 is the mass for the whole compound. But now we are going to first get the we are going to use the atomic masses for each of these, and then we shall see how we can use that mass later on. So if you use if you look at step 1 here, if you convert the percentage to grams, you can also give us the same computation, because this percentage can also be computed in terms of the grams, because we know that the compound will have a total percentage of 100, so you can equate this one to 100 grams. So which means instead of writing percentages, you can also write them as the grams. So instead of saying 4.07%, we can say 4.07 grams, and so on and so forth, as we just in the table. So we can divide those masses with their atomic masses. Even if you divide the percentages, we won't change it, but let us use the masses. So we know that now the moles will be giving us the mass divided by the atomic masses. Why are you getting these moles? So in step 2, we are going to do that. We decided we can get the moles that will give us the simplest mole ratio later on, because we shall get the moles of hydrogen as 4.07 divided by 1.008. That's the atomic mass of hydrogen. And then moles of carbon, 24.27 divided by 12.01. Those are the moles now of carbon. And then chlorine, do the same thing, 71.65 divided by 35.45 grams. And now we are getting the moles as 4.04, 2.021. And then in step 3, we shall divide with the smallest mole to get the mole ratio. So if you divide the smallest moles of this, we can say now, because now the smallest is 2.021, so we're going to divide the smallest on each of them, and it will give us the simplest mole ratio. if we divide with the smallest. So now we have this. Let us divide them as we see here. So it's now 2.02 we are going to divide on each of them. So that is in step 3 now we do that. For hydrogen, 4.04 divided by 2.021. For carbon, 2.021 divided by 2.021. And then do the same thing for chlorine, 2.021 divided by 2.021. And we shall get our ratio as 2 to 1 to 1. So that means we can now get our empirical formula. So the empirical formula now, we shall use this ratio, and to now be H is going to have 2, carbon is going to have 1, and chlorine is also going to have 1. So which means we can write our formula now, the empirical formula in the last step, step 4. Our empirical formula now will be written as C. Okay, we can say H2CCl, or you can start with the ones that you want. But now, if you want to use that order, it's also okay, and that will be our empirical formula. But you can say CH2Cl. That is our empirical formula. So that is our first example. We can also try now to get the molecular formula of this compound. We can get the molecular formula from the empirical formula. How can we do this? So now, since we know that the empirical formula multiplied by n factor will give us the molecular formula. So since we know the atomic masses, we can multiply these atomic masses with these ratios we have got. So the atomic mass of 12.01 plus 2 times the atomic mass of hydrogen, then plus 35.45 times 1. So which means we shall get 49.48 grams. So that is the simplest mass for that. So if you get the molecular mass divided by the mass that we have got in our empirical formula, it will give us the factor we have talked about, because the n will equal to the molar mass divided by the empirical formula mass, which gives us a 2. So which means our n is 2. So if you multiply our empirical formula with the 2, because we have said empirical formula multiplied by a factor, it will give us a molecular formula. So we shall get our molecular formula as that. Now, in this second part of the video, we are going to calculate reacting masses. How we can get a mass of the other if we are given one of the masses in an equation. So the example we are using here, they're telling us to calculate the mass of iron oxide produced when 45 grams of iron reacts with oxygen in excess. So we are given a balanced equation where we have 4 moles of iron are reacting with 3 moles of oxygen to get 2 moles of iron oxide. So what we start with here will be looking at the major important things that are going to be considered here. We are only looking at the iron because we are given the mass of iron. And then we are also looking at the iron oxide because it is the one we are going to calculate its mass. It's the one required. So if you look at our equation, the mole ratio is going to be 4 to 2. You're having 4 moles of iron giving you 2 moles of iron oxide. So let us only consider those that are really required. So when we need the mass in grams of iron oxide, and you're given 45 grams of iron. So those are very important key points in this calculation. Now, let us look at a simple formula here after writing the mole ratio as 4 to 2. We know that in our formula, we can calculate the moles that reacted. the moles of iron that reacted can be got from number of moles will equal to the mass over the atomic mass. Now we know that the mass that reacted here is 45 grams. And we know from the periodic table that the atomic mass of iron is 56. So we can look at the periodic table if we've forgotten it, and you can see the mass of iron as 56 from our periodic table. So we can write it there. Now we can say the number of moles will equal to mass over the atomic mass. And it is going to be 45 over 56. When we divide that, you get 0.80357. The values continue, but we shall round it off to 4 decimal places, and so 0.8036. So now we know the moles that reacted in that mass. So which means we are going to look for the moles that were produced of iron oxide. Okay? So we can do that here by looking at our mole ratio that we have just got 4:2, which means that you can see that we need more iron than the iron oxide according to the mole ratio. It is half. It will be 4:2, which means twice more iron is reacting in here. So that means you need half of these moles, as you see. So if you say 4:2, now 2 over 4, that means you're having half of that. So 0.8036 will be giving us half of that value. That's 2 over 4 times 0.836 will be giving us 0.4081. So you need 0.4018 moles of iron oxide. Okay? So if we go back in our formula, as number of moles will equal to mass out of the atomic mass or the molecular mass, we can now get the molecular mass of iron oxide. Because we know from our periodic table that the iron is 56, so we multiply by 2 because we are having our formula as iron 2, oxygen 3. So that means we shall multiply the iron by 2, that's 2 times 56 plus 3 times 16, and we get our molecular formula as 160. Okay? So this now we can say that from our formula, 0.4018 will equal to m divided by 160. And that will give us, if we arrange, that means m will equal to 0.4018 times 160. And we can get the mass that is required as 64.2857 grams. Okay? So if you try to round this off to 3 significant figures, it will give you 64.3 grams of iron oxide. So that's how we can use this concept to get the mass that reacted in this procedure. Of course, we can try other methods. If you don't want to calculate moles, you can do it directly by multiplying 4 times 56, and then also say 2 times this formula mass, and you can still do the same. We can get the same answer because it means you'll say 4 times 56 grams of iron reacted to give us 2 times 160 grams of iron oxide. Then what about 45 grams? What mass did it give? You can also use that method and you get the same answer as 64.3. Thank you. And this final part of the video, we are going to calculate reacting volumes. We are going to use a formula, volume of a gas will equal to moles times 24. This 24 is now the volume at room temperature, 24 decimeters cubed. We can say that if you are given, say, 3.5 moles of chlorine, and you want to get the volume that reacted, you can say 3.5 times 24 and you get 84 decimeters cubed. You can use the same thing for, let me say, oxygen. Assuming you are given 60 decimeters of oxygen and you want to get the moles, you just change the formula. And now say the moles will equal to the volume divided by 24, which gives you 60 divided by 24 and you get 2.5. You can also use an illustration. If now you have 27 grams of water vapor and you want to get the volume, you can still do that by saying that now we know that if 27 grams of water vapor really reacted, you can get the atomic mass or the molar mass by saying water is now going to be oxygen 16, hydrogen 2. So you say 16 plus 2. Oxygen is 16, water is 1. So you say H2O now will be 2 times 1 plus 16, which gives you 18 grams. So which means that the moles will be mass out of the molar mass or atomic mass, which is going to be 27 out of 18, and you get 1.5 moles. So after getting moles, now it becomes easy because now you can see the volume will be the moles times 24, which is going to be 1.5 times 24, and you get a value which is going to be 20. So you can get that value, which is 1.5 times 24, gives you the volume that reacted, and that volume now can be got as let me use my computation here very fast, and we can get the value, which is 1.5 times 24 is 36 decimeters cubed. Okay, so what if now we try another illustration where you are going to be looking for the volume of the product for a given, if you have the volume of the reactants, assuming we are having nitrogen reacting with hydrogen to get ammonia. There is 18 decimeters cubed of nitrogen reacting in excess. What will be the volume of ammonia? So we get the balanced equation where we have nitrogen plus 3 moles of hydrogen giving us 2 moles of ammonia. So if you use this equation, you can see that already we have seen that the 18 decimeters cubed of nitrogen, and we are looking for the volume of ammonia. So which means, look at the ratio. It's 1 to 2. So which means we are going to use this ratio to help us get the volume, because now we are moving from volume to volume, which means you just multiply 2 times 18 and you get 36 of that reacted. So if you look at this kind of equation, we know that you can also look at it in this way, that if you are moving from if you talk about 0.75 moles of nitrogen, that means you would have 0.75 times 2, which gives you 1.5 moles of ammonia. You see that? So 1.5 moles of ammonia times 24, so you get 36 decimeters cubed. Still, that idea can take you in the same kind of calculation if you're looking for the volume of the product that reacted. If we changed and said And nitrogen reacts with 3 moles of hydrogen to get 2 of ammonia. And now we are given 24 decimeters cubed of nitrogen. Find the moles of hydrogen. That means now the ratio is going to be 1 to 3, because now 1 mole of nitrogen with 3 moles of hydrogen. So to get the answer, I shall just say 4 times 3 and you get 12 decimeters.